Save everything. Let me remind you, this stuff you already know. Final is a week from today, late at night. Most of you should go to the Union Auditorium. There's a problem session Friday afternoon at 2:15 over in Javits. And today is a Wednesday, even though it says Monday on your calendar. What? No? Okay. So, if there's, what we still have a lot of stuff left to review. I'm not planning to review differential equations unless people want me to, because we just did that. So really, where we left off in the review was volumes. So I don't need to cover volumes anymore, right?
I don't know this morning.
Huh? Series? Okay. So let me just remind you what we're skipping. Work. Do work. All right, we'll get to work. So work is almost the same as volumes, except for the setting up part. So it's the integral of the force over the distance that the force is applied. So most of these problems that people, from start, finish. So a simple work problem would be something. So a very simple version would be something like you have a force which is, I don't know, 3x squared. So, and then you want to move, so x is, say, the distance. You have some, let's make it 3 over x. 3 over x squared. So that would be something like we have some object here. Say we have a magnetic charge that's repelling, and we have a magnet that we want to move in here, where x is the distance. And we want to know how much work it would take to move it from 3 units away to 1 unit away. So this would be very simple. It would just be the integral from 3 to 1. The reason it's negative is because the integral will be negative and the work needs to be positive, of 3 over x squared dx. So this would just be what is that? 3x to the minus 2. So that's negative 3 over x, evaluated from 3 to 1, which is negative 3 minus, what did I do wrong? Yeah, minus 1, plus 1. Okay, so something's wrong here.
The 1 should be before the 3.
Well, yeah, except the force is the other side. Okay, so we integrate from 1 to 3. So then that gives me, no, that was right before, wasn't it? Yeah, right, 3 to 1. Sorry. From 3 to 1, so this is negative 3, negative 1, I keep doing the same thing. Negative 1 plus 3 is 2. So it takes 2, whatever the right units are. So these are simple. The idea is exactly the same. The difficulty that people always have is calculating the force. So if I tell you the force and set up the problem, you just integrate. That's easy. The difficulty that people have is, what is the work that it requires to pump water out of a tank? Or what is it the work that it requires to stretch a spring? Or something like that. So that's where the hard problems come in. Right? But the idea of work is very simple. You're just calculating how much work, how much effort is this, how much force do you need to do that, and so on. Okay? So instead of a problem like this, you tend to see things more like, I don't know, would you prefer moving something, or a spring problem, or what?
Somebody saw this on test.
All right. You want some, okay, so how much work is needed to pump, I don't know, water out of a conical or other shaped tank, which is, let's say, height equals, I don't know, 12 meters. The radius, let's say the diameter at the top is, I don't know, 6. And let's just say it's completely full. Well, let's make it be half full. So it's full to a depth of 6 meters. And we need to know that water has a density of 1 kilogram per cubic meter, and we need to know the force of gravity is 9.8. There's that in feet. 9.8. And we need to know anything else? That's really all we need to know. So this is really a jazzed up volume problem where we're computing not exactly the volume of this surface of revolution, but we're computing the force that we have to use to lift something. So in terms of the picture, this distance is 12. Here we have 6. Here we have 6. We have this much stuff, and we want it to go out. Okay, do you want the spout to extend, or do you just want a spout where it will pour off the top? Extend. How long would you like the spout to be? 2 meters. Okay. I don't understand why that makes it harder, but it seems to. Okay, so we have a 2-meter spout. I don't understand why the spout makes things difficult, but it seems to. Okay, so what do we have to figure out? Well, I'm just going to draw the same picture again, but in cross-section. So this is 12. I'm going to now label this as 3, because twice 3 is 6. If we have a piece, a little slab of water at height y, so what we need to calculate is how much some water at height y needs to travel. Here's my spout, that's 2. So how far does a slab of water need to go? And what does it weigh? Because that will tell us everything, because we need to know the force we need to lift this, so that means we need to know how heavy is it, and how far do we have to move it. So, this little slab of water at height y looks like a little disc course, the sides are sloped, but we can ignore that. Of thickness dx, or dy. The radius here, we don't know the radius. We want to find that. That's r. And we can use the fact that it's at height y. So we have similar triangles here. The height of the tank, since it's a cone, the height of the tank to the radius of the tank is 423. So that means that this little triangle here is of height y, and why did I say 4 to 3? 4 to 1. So the radius is y over 4. Okay. The triangle. So we have r is to. How about y is to r is the same as 12 is to 3, because these are similar triangles. The distance from here to here is 12. The distance from here to here is 3. The distance from here to here is y. The distance from here to here is r. So the ratio of this to that is the same as the ratio of this to that. So that means that cross multiplying r equals y over 4. If we had a different shape, we might use a different method to figure it out, but okay. And so that means that the volume of this is dy times pi r squared volume of this little thing. And the distance it has to go is the distance from the very top, which is 14, from y to 14. So I guess I'll go over here. From the height y to the height 14, which is the top. So this is really 12 plus 2 more for the spout. And so that means that our integral, well, we integrate the mass of the stuff, which, since the density is 1 times pi y over 4 squared times the force due to gravity, which I guess is 9.8. So this is the volume. This is the density. Huh? I'm not doing it in grams. I'm doing it in kilograms. What? Okay, then it's 1,000. And 9.8 and dy. Oh no, times the distance it has to go, which is 14 minus y, dy. And how much do we have to move? Well, we have to move the stuff at height 0 all the way up to the stuff at height 6. What's that? Now, do you want me to do that integral? I mean, it's square it out, go for it. I'll do it if you want. Just keep it calling up. If it were a sphere, we would have a different formula, which would mean that we would calculate this little slab r differently. If it were a pyramidal box, then we would have yet a different formula for the variation of the thing. This is exactly the same concept exactly the same concept of finding volumes of surfaces with a known cross-section. The only difference is we have to multiply it by the distance it needs to go. That's it. It's exactly the same. Stuff with the spring, exactly the same. You just integrate the force over the distance it needs to be applied. Okay? Do I need to say any more about work? Yeah?
How come we didn't split it into two integrals from, say, 0 to 12?
Okay, if you'd like, I can integrate from 0 to 6, and from 6 to 12 of 0.
I meant, and then from 12 to 14.
Plus the integral from 12 to 14 of 0, if you want. There's nothing you have to do. There's no water above the height of 6, so it has nothing to do. So if let's make the problem harder. Suppose this is a mixture of oil and vinegar. So the oil is at 6 and the vinegar is from 6 to 12. Then we would have two integrals. We have one for the work to lift the oil. No, oil flow. Sorry, the vinegar is at the bottom. No. Yeah, the vinegar is at the bottom, so we would have a different density. So we would integrate from 0 to 6 at the density of vinegar, and then the density from 6 to 12 for the oil. But other than that, it's the same. Yeah?
But don't you have to cut the water out, or allowing it from the middle to
Because there's no water that needs to go out between here and here. So look at, just consider one little slab of water. Okay? So it's hard to think of a slab of water, so think of this as plastic. I'm going to shave it up. So I chop it up into a bunch of little slabs, and the work to lift this slab from here to there is this. The amount of work, the amount of effort I need to expend to lift this little cylinder at height y is, it needs to go from here to here. That's 14 minus y meters. Yes? Okay? From here to here, 14 minus y meters. How heavy is it? Well, it depends on how big it is. How heavy is it? Well, it's this times, and then I need the 9.8 from gravity. So that's how much work I need to do just for this skinny little slab. The integral is letting me add up all the skinny little slabs. So there's a slab here at height 1. There's a slab here at height 1/2. There's a slab here at height 5. Each of those causes me to do a little bit of work. Up here, there's no slab. There's no work to do it.
So why are you supposed to be doing the water out of the
That's where this comes in. If I put the spout right here, then there would be no work to take out this one. And in fact, if I put the spout here, then there's no work at all. I just open the tank, it's negative work. Because I can put a little generator on here and get some energy out of it. So integrals let you add up things. What am I adding up? I'm adding up the energy, the work I need to do a small thing. I have a lot of small things, all of these slices. So I'm adding up the work for each of the small slices. The integral is not telling me the amount of work for any one of the slices. The integral is letting me sum up the work for all of the slices. People are still confused, I can see. I don't know why. Okay. Do I need to say more about this? I don't think that will help. Okay, let's move on. We talked about arc length. We talked about average value. I think we've done all of that stuff. So we can move on to series. Okay. So. I suppose I should say something about, do I need to say anything about sequences? They are just limits. So we have two objects, one of which we pay a lot of attention to, one of which we pay little attention to. So if we see something like this, I, this is just a list of numbers. So something like 1 over n equals 3 to infinity just means 1/3, 1/4, 1/5, 1/6. Just a sequence of numbers. So this is called a sequence. And the typical question is, does this converge? So that's really just a limit question. So if we say, what is the limit of the sequence 1 over n? Then you calculate limit as n goes to infinity of 1 over n, which is 0. So this guy converges. The only difference here is these functions only take on integer values. So if we asked about something like the limit of sine of 2 pi n, well that's 0 even though the limit of sine n doesn't exist. So this is easy. Anybody have any? So the biggest confusion that people tend to have is they answered the wrong question when they're asked about a sequence. They say, oh, we have to use the ratio test or something. Those are for series. So one object we have is sequences. This is a tool we use to understand infinite series or sums. So this might make an appearance. It's small, even though it's fundamentally important. So something we spend more time with is the idea of infinite sums, which are also called infinite series. Series is the more common word. I prefer the word sum because of the meaning in English. Sum makes it clear you're adding. Series is confusing to people, but too bad. This is the word that people use. And we tend to write them with sigma. We use n. Something like about 1/3 to the n. Something like that. So for infinite sums, so this means take n equals 0. So we get 1/3 to the 0, which is 1. Then take n equals 1, which means we get 1/3. Then take n equals 2, means we get 1/9. And take n equals 3, we get 1/27. And keep doing that forever. And then the question is, does this add up to something? That's a 9. Does this add up to something? Or does it get big? Or does it do weird stuff? And that's what we're trying to solve. So for series, this one that I wrote down, so there are some special types that we know how to add up. So for example, the geometric series looks like, well, so one that we have the formula for starts at 0. N equals 0 to infinity, some constant. Is it usually A? I guess it is. Yeah. Some constant times the ratio to the nth power. It's not hard to figure out the formula that this is A over 1 minus R. If R is less than 1 in absolute value. So this one, A is 1, and R is 1/3. So this guy adds up to 1 over 2/3, which is 1.5. You definitely should know how to sum a geometric series. It's important to remember the geometric series start at 0. So if you see a geometric series that doesn't start at 0, then you either need to adjust A to absorb it or somehow otherwise manipulate it to make it look like that. There are also sometimes telescoping series, which would be something like, so let me remind you, really what we're doing with an infinite sum is we are calculating what do we get when we add the first term? What do we get when we add the first two terms? What do we get when we add the first three terms? So we turn this series into a sequence of partial sums. So in general, what we're looking at, the sequence Sn, which is I add from, let's call this Sk, which means I add starting at 0, or whatever the first term is, up to k. So I take A0, A1, A2, and I stop at the kth term. I call that Sk. And I want to say, does the resulting partial sum does the resulting sequence, does this converge? That's really the question we're asking when we're looking at an infinite sum. Does the resulting sequence that I get when I add things together converge? So for a telescoping guy, we might have something that looks like, let me leave it factor. That looks like this, where each term kills off part of the previous term. If we write out terms for this, we get 1/2 minus 1 plus, did I do this backwards? Yeah, so this one doesn't work, okay? This one's not telescoping. So then I get 1/3 minus 1/2. Maybe it does. Then I get 1/4 minus 1/3. Oh, this is okay. And so on. And what happens? Well, if I stop at any stage, notice that, well, I have this minus 1 always. And then I add 1/2. So if I list the partial sums, S1 is negative 1/2. S2 is, well, if I just take the first two, then this 1/2 kills that 1/2, leaving me minus 1 plus 1/3. S3 is minus 1 plus, well, this 1/3 kills that 1/3, but it leaves a 1/4 in its place. And so on. And if we look at the last, Sk, well, not the last, but if we go for a long time, we get minus 1, then the 1/2 kills off, then the 1/3s kill off, then the 1/4s kill off, then the and then we're left with the one that didn't get killed off. So if we look at the limit, as k goes to infinity of the partial sum, this is the limit as k goes to infinity of minus 1 plus 1 over k, which is just minus 1. So we have just the first term. Yeah? Oh, okay. Yes, you're right. Doesn't make a difference. The limit's still the same. I just wrote it down wrong. Right? S3 is minus 1 plus 1/4. Sk is minus 1 plus 1 over k plus 1. So thank you for fixing that. But still the limit is minus 1. Of course, I can fool you in some sense by making something here where this last term doesn't go to 0. Right? Where it still kills off the earlier terms, but this thing is always non-zero, so the limit won't exist because maybe this thing will grow. So you have to look a little more carefully. You can't just say, oh look, stuff cancels out. Here we go. So for example, this guy converges to -1, but if we look at, well, I don't have one in mind right now. Shoot. Oh, it's okay. All right, so we have these telescoping guys that may cancel out. But in general, it's often hard to find sums directly. So, so we develop, just like we did for integrals and just like we did for derivatives, we develop techniques to put things together. So the various tests we do to see whether things converge might be the integral test. So even if we can't add it up, we might just ask, does it add up? And then if it does add up, then we can approximate it by something. So, for example, one thing we develop is the integral test. This says that if, well, let's just say, instead of if, let's just say the sum from n equals whatever of an and the integral from whatever of an dn. So just you look at your term and you integrate it, these do the same thing. If the improper integral, which you get when you integrate the nth term, converges, then so does the sum. If the improper integral diverges, then so does the sum. The integral test, conceptually, is pretty easy. Just integrate the term. I guess we also see, let's call it a divergence test, which I should have said first. If the limit as n goes to infinity of an is not 0, then the sum diverges. If it is 0, you don't know. But if the limit of the nth term is not 0, then the thing diverges. If I'm ultimately adding 1 all the time, then I'll get a lot of stuff. The integral test here, this is for positive terms, or non-negative terms. I wrote integer. Good. And I wrote it on a board I can't lift. Also good. So, do I need to, I'll leave that up for a minute. I'll look over here. Running low on time, I'm sorry. Do you need me to list all these tests? Yes? Keep going? Well, because we have finite time. But okay, I'll keep going. So we have the integral test. For once, another one that we have is, say, the comparison test. So Again, this is if we have a series of positive terms. Then if we have something smaller that we know about, and that smaller thing diverges, then so does the bigger thing. If we have a bigger thing, and the bigger thing converges, so does the small thing. Now we need to have some things in hand to compare to. So one thing that you get right away out of the integral test is a class of series called the P-series. One over, what am I doing? Yeah, 1 over x to the, do we write it as x to the p or 1 over x to the p? I guess it doesn't matter. So here, if p is bigger than 1, if I write it this way, from n equals anything to infinity, what did I just do wrong here? 1 over n to the p, that's the problem. Here, if p is big, then this converges. If p is small, it diverges. So if we have a sum of powers, P stands for power. If we have a sum of powers, and those powers are big, then the thing converges. That follows immediately from doing the integral test on this. We integrate 1 over x to the p. You see that if p is big, you get a number. If not, you don't. And so that gives us a big class of things to compare with for the comparison test. Unfortunately, the comparison test isn't always easy because it's sometimes hard to locate something to compare with. So maybe I should just do 2 quick examples. So for example, if I want to know what about the sum n equals 2 to infinity 1 over n cubed plus, let's see, do I want a plus here? So that's smaller. So if I wanted to know about this, does this converge or diverge if I use comparison? And what do I compare to? 1 over, oh yeah, that was a cube. For some reason I thought it was 5. Okay. So we compare with 1 over n cubed. Does that tell us whether it converges or diverges? Okay, so this converges for 2 reasons. Since 1 over n cubed plus 5 is always less than 1 over n cubed, and the sum of 1 over n cubed is a p-series. On the other hand, if I have something like, just change that plus to a minus, I can't now use that. I still want to say it converges. So I can compare it to 1 over n squared, but I can always say, well, this looks like 1 over n cubed a whole lot. So there's a version of the comparison test called the limit comparison test. which says that if I look at the limit of the ratio, and this is not 0 or infinity, then AN and BN do the same thing. So if you know, if the things look the same for big N, then they do the same thing. So here, in this case, I would use limit comparison. So I would look at the limit as n goes to infinity of 1 over n cubed over 1 over n cubed minus 5. That limit's 1. And so limit comparison says that the sum over 1 over n cubed minus 5 converges just like 1 over n cubed, because that's a p-series that converges good. Okay? I guess the other test that we had is, so all of these are for positive term series. Sometimes the terms are not positive. So we might have an alternating series. This is one that the signs alternate. What do I want to use? Okay. And alternating series are particularly easy because you can use the alternating series test. So the alternating series test says if the absolute, well, okay, if the absolute value of the terms, so if the series is alternating, so plus, minus, plus, minus, plus, minus, and the absolute value of the terms, well, that are decreasing, so let's make it this way. Yeah, I guess that can decrease. And the limit of these terms is 0, then this converges. One other thing we get out of the alternating series, which we also get out of the integral test, but I didn't write it down, is not only does it converge, but we know if we stop after k terms, then we're off. So, for the alternating series, we not only get that, but we get that if we add up, so for alternating series only, if we add up and stop somewhere we're off from what we would get if we went up to infinity by no more than the term we didn't use. So, for example, let me put them both together. Let's do the most straightforward alternating series. The alternating harmonic series. So this is minus 1 plus a half, minus a third, plus a quarter, minus blah, blah, blah. This guy converges. Even though if I change all of these to pluses, it diverges. This guy converges by the alternating series test, since 1 over n plus 1 is less than 1 over n, and the limit as n goes to infinity of 1 over n is 0, so it converges by the alternating series test. And if I stop after 100 terms, so I do minus 1 plus a half, minus a third, plus a quarter, and I do it for a long time, and I stop at 1 over 100, then this is off from if I go to infinity less than 1 over 101. Because the term I didn't use controls everything. All the rest is smaller than that. The sum of all the rest is smaller than that. Okay, so all of this was a setup to be able to do Taylor series and Maclaurin series, which I have to cover now in 6 minutes. Or power series, I guess. Oh, I missed the ratio test. I'm sorry. When I was writing tests, don't forget the ratio test. Let me write it here. Again, if the limit as n goes to infinity of the sum, not the sum, of the next term over the current term is less than 1. So if the ratio of the next term to the current term is less than 1, then this thing goes faster than a geometric series, so the series converges. And in fact, it converges absolutely, which means that both the series and if we change some of the sign, it still converges. If this limit is bigger than 1, then the series diverges. And if it equals 1, you have to try something else. So the ratio test gives you no information when the ratio is 0, when the limit is 0. Is 1. Compare that to limit comparison, which was somewhere, is here, which works when the ratio is 1. So you have to keep track which is which. But, okay. So the ratio, for me, the two most useful tests, well, alternating series because it's easy, so the 3 most useful tests, the 4 most useful. I find the ratio test, limit comparison, most useful unless there's something obvious like an alternating series or something like that. If I'm just handed a test, a series out of the air, the first thing I try is I say, can I compare it to something? Let's try limit comparison. If I don't see what to compare it to, I try the ratio test. If that doesn't work, then I have to work harder and do an integral or something. Okay, so let's see if I can get Taylor series now in 1 minute. So, for power series, we can, or for often we can write a function as a sum of something involving x. Let me just write it this way for a minute. So we can write some function where the terms all depend on x. Usually, this will be a power series that looks like some number times some power of n. So, we can do that. The nice thing about, say, Taylor series or Maclaurin series tells us how to find these coefficients. So, Maclaurin is just Taylor series. I shouldn't have used C. Oh well. Where we're expanding around 0. It tells us that the function is, well, it's its value at your favorite point, let's call it A, plus the derivative at that point times how far off you are from that point, plus the second derivative at that point divided by 2, how far off you are squared, plus the third derivative at that point. I don't have enough room. I guess I go on to the next board. So maybe I can write it here. Plus the third derivative divided by 3 factorial by how far off you are cubed. Blah, 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 blah. So in general, the nth derivative over n factorial by how far off you are to the nth power, and then you keep going. So for Maclaurin series, A is 0. So you can do this for a lot of series. You should know, definitely should know, the Maclaurin series for e to the x, for the sine, for the cosine, for a geometric series, say for the log. I mean, this one you can get from that. Do I need that one? I mean, this one you can get easily from that one. That's pretty much it. You can get the other. So if you know these, you can get pretty much all the other ones. We can get them by, say, integrating and differentiating. Yeah. Could be on either, depending on how I say it. So, for example, a reasonable thing on the easy part would be, tell me the Maclaurin series for sine of 2x. That should be easy, because you know the Maclaurin series for the sine of 2. I mean, for the sine of x, and you put a 2 everywhere you see an x. Something harder might be, give me the Taylor series for the sine of 2x expanded around x equals pi over 4. That's harder. Or of x squared sine 2x. Or of the integral of sine x over x. Or something where you have to do more work. So the easy part would be, tell me one of these or a minor modification of it. The hard part would be a major modification. You see the difference? Okay. I'm out of time, so what I recommend you do, since we're out of time, is if you have more questions, I will be around, but I'm not scheduling office hours this week. If you want to come see me, send me an email, give me a call, I can set up a time, post questions on Piazza, stuff like that. I'm holding the review session, well, the problem session on Friday. So I'm done reviewing now. If you want more reviewing, you can go bother with this one. And we want to know how much work it would take to move it from 3 units away to 1 unit away. So this would be very simple. It would just be the integral from 3 to 1. The reason it's negative is because the integral will be negative and the work needs to be positive of 3 over x squared dx. So this would just be, what is that, 3x to the minus 2. So that's negative 3 over x, evaluated from 3 to 1, which is negative 3 minus, what did I do wrong? Yeah, minus 1, plus 1. Okay, so something's wrong here.
The 1 should be before the 3.
Well, yeah, except the force is the other side. Okay, so we integrate from 1 to 3. So then we're moving something, or a spring problem, or what?
Somebody saw this on test.
All right. You want some? Okay, so how much work is needed to pump, I don't know, water out of a conical or other shaped tank, which is, let's say, height equals, I don't know, 12 meters. The radius, let's say the diameter at the top is, I don't know, 6. And let's just say it's completely full. Well, let's make it be half full. Save everything. Let me remind you, this stuff you already know. Final is a week from today, late at night. Most of you should go to the Union Auditorium. There's a problem session Friday afternoon at 2:15 over in Javits. And today is a Wednesday, even though it says Monday on your calendar. What? No? Okay. So, if there's, what we still have a lot of stuff left to review. I'm not planning to review differential equations unless people want me to, because we just did that. So really, where we left off in the review was volumes. So I don't need to cover volumes anymore, right?
I don't know,
Huh? Series? Okay. So let me just remind you what we're skipping. Work. Do work. All right, we'll get to work. So work is almost the same as volumes, except for the setting up part. So it's the integral of the force over the distance that the force is applied. So most of these problems that people, so from, start, finish. So a simple work problem would be something, so a very simple version would be something like you have a force which is, I don't know, 3x squared. So, and then you want to move, so x is, say, the distance. You have some, let's make it 3 over x. 3 over x squared. So that would be something like, we have some object here, say we have a magnetic charge that's repelling, and we have a magnet that we want to move in here, where x is the distance. Gives me, no, that was right before, wasn't it? Yeah, right, 3 to 1. Sorry. From 3 to 1, so this is -3, -1, I keep doing the same thing. -1 plus 3 is 2. So it takes 2, whatever the right units are. So these are simple. The idea is exactly the same. The difficulty that people always have is calculating the force. So if I tell you the force and set up the problem, you just integrate. That's easy. The difficulty that people have is, what is the work that it requires to pump water out of a tank? Or what is it the work that it requires to stretch a spring? Or something like that. So that's where the hard problems come in. Right? But the idea of work is very simple. You're just calculating how much work, how much effort is this, how much force do you need to do that, and so on. Okay? So instead of a problem like this, you tend to see things more like, I don't know, would you prefer